Welcome to Programming in Modern C++. We are in week 8 and we are now going to discuss module 37. In the last module, we started talking about error handling in C and C++ programs, and we discussed the variety of mechanisms that the developers engage in handling errors in C. Most of them come from a set of different standard library headers, and none of them are complete support, but a judicious combination of them depending on different contexts must be used to provide a good error handling support in C. We also introduced the concept of exceptions formally, and making little distinction between errors in general and exceptions which are unexpected and infrequent, and demonstrated with examples. We will continue on that in this second and concluding part of error handling discussions, particularly focusing on what C++ provides. How does C++ actually introduce a single exception handling mechanism to encompass all kind of situations that may arise in terms of synchronous as well as asynchronous errors in a program. This outline will be available on the left panel, as you know. Now, let us walk straight into discussing exceptions in C++. These are few characteristics that are desirable and incidentally are supported in C++. The first thing is it allows to separate the error handling flow code from the normal code. In C, this was not possible. As we saw, they are all mixed up. Here, exception flow and the normal flow are separated in the program at separate distinct spaces. It is a language mechanism rather than support from the standard library as we saw in C. The compilers can track automatic variables, and as is required in C++, it can do the destruction of automatic variables when, because of error, without following the normal flow, the control has to go out of a certain scope. It has schemes for destruction of dynamic memory. It provides naturally much less overhead for the designer, the developer, the programmer to take care of different error and exception situations in the program. It can come out of deep levels of nesting by propagating the error in an appropriate way, which we saw we were kind of trying to do using local go-tos. We do not need to do that anymore. Exceptions support this kind of proper exit from the deepest level of nesting, and various exceptions can be handled by a single handler. So, these are the expectations, and they are rightly met by the exception handling mechanism in C++. So, here is we start with putting in parallel the C solution for exception handling, which is closest to the C++, the non-local go-to, and the C++ solution. So, in terms of non-local go-to, we know that we need to include this header, define a buffer to keep the environment of the caller, and in the caller you do a set jump to set the environment, and then you proceed in terms of the normal flow. The function is called and the function continues. Now, if there is an error, then a long jump is executed, otherwise the function continues as it is and returns to this point, right, the statement after G. But if there is a long jump, that is, if there has been an instance of error which you are raising, as in here, then the control that had gone from main to G will come back to the exception part, to the handling part, which is what the J buff, the jump buff environment context helps us to do. Naturally, this means that if we have different kind of errors, different functions, or within the same function different long jumps to be done to different contexts, then we need to set different buffers. Now, in C++, this has all been made very simple. You just need to write the code, this equivalent code as in here, within a pair of curly braces and prefix it by try. So, the sense is you are saying that I am trying this code out, there may be some issues. It goes normally, calls G. If there is an error, it will throw. If there is no error, it will return to the designated point. If there is an error, then it throws, and when it throws, it directly comes to what is written as catch, known as the catch clause. So, we call this mechanism try, throw, catch. You try out a code, if the code does not behave, it will throw, and if it throws, it will be caught by the handler to do subsequent things. This is the basic mechanism. Now, if we look at the throw has to throw an exception object. This exception object is one where the callee can put enough information for the caller to proceed. So, you will typically have a class defined for this with the appropriate behavior that you need, and you construct. So, this is, as you can see, this is a kind of a almost an explicit call to the constructor, which is which will prepare an exception object, unnamed exception object, which will be thrown and be caught here by this type. Right? You can any kind of exception object can be thrown. It can be an integer, it can be a character, it can be your own class, but it is often customary to specialize from a library provided, standard library provided exception class, which has some well defined behavior. We will see what those behaviors are and use that. You can use your own exception class as well. Now, with this, let us see what will happen in terms of the try catch, try throw catch. Naturally, if there is no error, as I said, if there is no error, the simple thing is it calls, it returns to the next statement. So, this will see out the called, see out started, see out ended, and see out returned. As you can see, G is called, G is successfully returned. There is no surprise, there is no difference in terms of the normal code that you see. However, if there is an error, now I am introducing as if there is an error. So, when the try from the within the try block, as I call G, G goes in, gets the error, executes. So, called has happened, started has happened, and then some logic happens and there is an error. It constructs the exception object and throws it. As it throws, the remaining part of the code is not executed. So, the process is G is called, exception is raised. Now, at this point the function would like to return the control back to the caller. Now, as you know, when the function is called, a stack frame is created for G, which has the local variables and all that, and when it has to get out, when it completes the task and gets out of that function scope, that stack frame has to be removed, maybe logically removed, not actually removed in terms of values, but you change the pointers in a way so that it does not remain the active stack frame anymore. So, when you are going out of the callee's context for a throw, an exception condition, the stack frame of G will have to be unwinded. It has to be rolled back, because after this the control will go to the caller and the stack frame of the caller needs to be activated. Now, what is the consequence of unwinding the stack frame? Is it just it is a stack frame. So, this frame was on the top. Do I just put the top of the stack below this frame pointing to the frame of main, and am I done? In C, that is what we assume, but that is not, that is what long jump will do. But in C++, the critical thing is there are several local automatic objects. So, I have just introduced some arbitrary class A and an object which is automatic in the function scope. Now, this object, certainly when the control passed here, this object was constructed. If I had a normal flow at this point, this object would have been destructed, but I am not having a normal flow. This part is not going to get executed. So, what do I need to do before the throw happens? Is to also destruct the object A, because the stack frame is getting unwinded. So, wherever the object A was, that is not a part of the computation anymore. So, this is a very, very important behavior of throw in C++, which is critical for the correctness of all live objects and their lifetime. Naturally, after that, remaining execution of G and the cout, these are skipped, and the control comes to the catch block, and the control, as it says, it's as if a ball has been thrown, and as the fielder does, we are catching that ball, we are catching that exception object thrown, and it is caught by the catch clause. Catch clause does whatever handling is required. In this case, we have not put anything except for a statement. So, the failed is given on the output, and then after this the normal flow continues in main. It has to decide what to do about the incomplete execution of G, whether it will call G again or call some other function and so on. All those are considerations of the developer. But this is all about the mechanism of try catch throw, which is very, very important for any kind of error handling in C++. Here I have given a kind of small but detailed example with different cases. As I always say, that I try to put some one slide summary of the important concepts. So, it is that kind of a slide. So, let us spend a little bit of time here. I have a my exception class derived from public exception, which is a standard library exception class coming in this standard library exception. I have another class, my class, which is just to create objects. Let us say we have a global, I mean, for simplicity I have not gone into member functions, I am just dealing with global functions. So, there are 3 global functions here, f, g and h, and naturally main. So, the flow is main will call f, which in turn will call g, which in turn will call h. and on this flow we want to see what is the effect of having different exceptions. Now, so H, I am sorry, I should not have erased this. This is important for you to keep in mind. So, H is the, in this code, H is the most deep call that I have. Within H, within the scope, I construct an object of my class. This is just for illustration of automatic variable handling. Then I have put in terms of comments, so that you can uncomment any one of them and really check out, throwing different types of exception objects. This is integer, this is double, this is my exception which is specialized from exception, this is unspecialized exception, the standard library exception, and even throwing the a my class object. In every case, you will have to construct the object and throw. If it is a built-in type, you can just throw the literal. Right. Now, one thing common that will happen when any one of the throw happens is, since the control goes out from the context of H, the object which was local automatic here will have to be destructed, and this will be destructed at this point. So, if you look at the caller of G, caller of H, because H was called from G. So, if H throws, it will go to G, that has put H in a try block, right, and it has put a number of catch clauses. Multiple catch clauses can be put. These are alternates to check what type of error has actually come, which type of exception object has actually come, and they are executed, they are tried out, not executed, they are tried out in this order. So, you first try to match the first catch clause. If it matches your type of the object thrown by the callee, if it matches the type given in the catch clause, that catch clause catches that exception, and rest of the clauses are skipped. But if it does not, then it moves on to the next catch clause, and this mapping does not use any implicit conversion or anything. It has to be either a perfect match, or it can match a specialized class for a class object for a generalized class object. That is, upcast is allowed, but implicit conversions are not allowed. So, what will happen if I think I will reduce this clutter little bit. Now, let us say if I have thrown line 1, the first catch clause is int. So, it will match here, and this handling will be done, that is int will be printed. If you did not uncomment this, naturally if you keep this uncommented, then the second throw you will never be able to see, but if you keep it commented and uncomment this one, then you have a double object coming in. So, in the catch clause, int will not match, rather it will go to the next, it is double. So, it will match here. So, the throw from the first line matches catch int, throw from the second line matches double. Then we have something which is interesting, which is called the catch all clause. This is called catch all. That is, after everything you have specified, at the end you can put a catch all clause which will match any type of exception object that has been thrown. So, there are three possibilities: my exception, exception and my class object. So, they will not match here, they will not match here. So, all of them will match in this clause. This is the catch all clause. Now, obviously, at this point with this catch all clause, you really do not know what type of exception object you have got and what type of exception has actually happened. So, what I show is that it is not necessary for the caller to be able to handle the exception in every case, which it could do for int and for double, but it could just throw it again. Right? It could just rethrow. This is called a rethrow. It just says throw. It does not say anything about the object, because it does not know the object type. It has not resolved the object type. So, whatever object it has got, whatever type it has, that object will be passed on. So, G will also have now an unwinding of the stack, because it is throwing. Right? So, if G unwinds, the control will go back to F, and before doing that, the local automatic object in G as a part of the stack unwinding process will get destructed. You can see the nice pattern that is being followed. Now, as G is thrown, so the actions on line 3, 4, 5 are not still known. So, as G is thrown, it comes back to F, which had called G under the try block. F has provided again 3 catch clauses in the order, but it has provided them by resolving the 3 types of exceptions that can actually happen. So, if I have line 3 exceptions from line 3 uncommented, I get a my exception object, and therefore, this is handled here. If I have line 4, that is exception general exception object, then it does not match here. Why it does not match? Because to match exception object to my exception object, I need a downcast. Mind here, this is the easier specialization. So, I need a downcast. A downcast is not permitted. So, it will not match here, but it will match at this point, and this handling will be done. Finally, if I have uncommented line 5, then I have my class, which obviously does not match here, it does not match here, and it will match the catch all clause again. Right? So, for line 5, I still do not know what needs to be done in sitting in F, because I am just catching it by it was not kind of expected to me. So, I am just catching it by catch all clause, and so what I decide to do is throw it again. As I throw it, the stack frame of F goes out of context. So, the local object automatic object of F is destructed, and the control comes back to main within its try block, which has just one catch all clause, because main does not want to do anything. Main just wants to say, okay, if nobody could handle something, then this is what we will do. So, possibly main will decide at this point that since it was not handled by the callees F, G and H, they could not decide that. Main has no means of doing anything, it will probably just terminate the program, but it depends. So, this is the overall mechanism that is involved in terms of the exception propagation. So, you could see that how from a depth of call you can propagate the exception nicely back to the topmost level, which is main, and in the process unwind the stacks as needed and clean up the automatic objects. But in case one of these functions could catch the right type of the exception, it will handle that and proceed from that point. It will not propagate it to its caller. Couple of points to note is if you consider the ordering of these two clauses, you must note that you cannot put this clause before the other one. That is, catch exception cannot come before catch my exception, because if it does, then when a my exception object is thrown, exception will always catch that by upcast, and my exception clause will never be actually obtained. So, you will have an upcast and you will just treat it as a generic exception, you will not get the specialized behavior. So, always the more general classes have to occur later, and by the extension of that same logic, your catch all clause must be the last one in the list of clauses, otherwise it will hide all other catch clauses that you have written. So, this is the overall exception mechanism, how it works in C++. Now, quickly on to some syntax stuff and basic definitions, just to consolidate. Now, try block is consolidates the area that might throw exceptions, right. If you do not put codes in the try block, the calls in the try block, you will not have catch clauses, and therefore, if such a code will throw it will automatically be thrown up to the caller, because certainly there is no catch clause associated. So, it is good to put that. There are two kinds of try blocks. One is what we have seen, which can be nested also. You can have one try block within another try block, that is do few things, then do something under try. If there is a problem, handle that and proceed. And in the overall, either here, or if you want to rethrow from the inner try block, you can always handle in the outer one. So, it can be nested, and there is something which is specially called a function try block, where the entire function body is put in the try block. In many cases that is done. Just it has the same syntax, except that in case of a function try block, the actual function block curly braces must not be provided. If you provide them, they become a normal try block. If you do not, then the compiler treats the entire try block as the function body, right. You can have returns from within that and so on, everything else is the same, but this is what is a different type of try block you can have. Similarly, catch block catches the exception. So, it has an exception argument. Normally, the exception argument is taken as a reference parameter, certainly because you do not want to unnecessarily keep copying the exception object, they are finally temporary. So, you take that as a reference, and also if you want, you can make it a constant reference if the context demands. So, it is basically the name of the exception handler, you can say. So, catching an exception is more like throwing an exception is like preparing the argument, and catching an exception is like calling a function. So, the body of the catch clause is kind of conceptually the handler function that is getting called, and it is unique with formal parameters for each handler, and it can simply have a type name if you just do not want any details from the object runtime instance. Try catch matching, I have already mentioned that most of them are exact matches. There is no implicit conversion that is allowed, but you can use upcast in terms of matching a specialized object for a generalized exception class. Of course, in terms of pointer type, the standard conversions will apply if you throw a pointer type of exception, right. You might need to do that, because if through the exception you need to really pass a lot of information which has to be persistent and so on. The order of they are matched according to the order of appearance. We have seen that base class catch clause precedes the derived class catch clause. We have seen catch all clause has to be at the end. All these we have seen, and finally, if no handler can be found even in the main, then the terminate is called. Terminate is a function which terminates the program. So, in terms of raising throwing, the exception is treated in the same way as a function argument. So, you are preparing the argument and then throwing it for the catch clause to call the handler. So, this is the exception context, throw exceptions as we have seen. You can create an exception object and then throw it, you can do that, you can create the exception object explicitly. So, these are different options that you have for this. Note that exception object is always created on the free store, right. The reason is simple, because the stack is being unwinded. So, there is no available stack frame, or there is no stable stack frame in which you can create the exception object. Naturally, you do not want to create it in the global space and clutter that. So, you create this as on the free store, it is dynamically created and will get destroyed when the exception has been handled or propagated upwards. So, there are certain restrictions that if you are using a user defined type for as an exception object, then you must provide the copy constructor and the destructor. Obviously, destructor is required so that at the end you can clean up. Copy constructor is required in case you want to rethrow, right. And any type can be used, but it has to be a complete type. You cannot have an incomplete type or pointed to an incomplete type usually, right. So, like I have just written class a forward declaration. I cannot use this as an exception type for the simple reason that I need constructor, destructor, copy constructor, all of these for the exception types. As we have seen that you can rethrow in two ways. One is, this is what we saw, you can just write throw, and or you have caught the exception and then you throw it again. There is a subtle difference in this. If you just do this, then no new exception object is created. Whatever was created is just passed on. Whatever was received is just passed on. But here, what was received will be copied, made a new copy of, and the original one will be destructed. That is where you need the copy constructor, right. So, these are the two differences. You have to decide which one will suit your purpose better. Certainly, lot of advantages of exceptions: destructor savvy, unobtrusive, precise, they are native and standard because they are part of the language. Now, these are the shortcomings that we had noted for C. Now, they are in C++, they are really the strengths. Besides that, this is scalable because each function can have multiple try blocks, each try block can have multiple handlers, each handler can have single or group of types, all types. It is fault tolerant because it makes functions specify what should be their error behavior and so on. So, exceptions are kind of a solution for all kinds of error handling. Now, coming to the standard library, what the standard library gives you? Standard library gives you this class which has an constructor. The writing throw with the parenthesis here says this is called no throw guarantee. That is, all these functions themselves guarantee that they will not throw anything, right. So, that otherwise you are trying to build that exception object and that throws, and again you are trying to build an exception object. So, this will be an infinite loop. So, these have exception guarantees. So, you have the constructor, the copy constructor, the copy assignment operator, the destructor, and a special what function where you can put a message that you can extract later on. Right. So, it is good to derive your exceptions, specialize your exceptions from this, so that the general interface remains the same. There are various specializations of this class exception. Broadly are runtime and logical errors, like runtime is overflow, underflow in arithmetic, logical is invalid argument, length error, out of range, and so on. Besides that, there are some of the special exception cases, like bad cast we have seen for dynamic cast, bad type ID we have seen for type ID. Bad alloc will happen when you are trying to do a new and there is not enough memory. If you have thrown a wrong exceptions, then you will get a bad exception and so on. So, it's a huge provision. So, this is what C++ 03 had, of which you just saw the simplified diagram. You have to really understand what these are and make use of them, because not in every case you need to throw your own exception. The exceptions will be generated by the system and you just need to pass it on. Going to the future later versions of C++, there has been several extensions to this standard library. So, which I have shown by different colors. This is just for your information. We are not going to discuss this or have it in the assignments immediately. when we do the modern part of the C++, we will talk little bit about some of them. So, to conclude, we have discussed about exception handling in C++ and illustrated try-catch throw features for handling errors with examples. Thank you very much for your attention. See you in the next module.